So what I like to talk about in this talk is essentially a minimal information for real-time decision making. And of course, any reasonable decision making process must be based on some sort of information. But what I'm really interested in this talk is the minimal information based on which the right decision making is still possible. So at least intuitively, there should be a fundamental trade-off between the amount of information that you're utilizing and the best decision quality you can achieve using that information. So since my background is actually control theory, I like to approach this trade-off study using basic tools from control theory and information theory and convex optimization theory. So this talk, I like to restrict myself to the LQG framework, which is, of course, a way too simple model, mathematical model to describe any reasonable real-world object. But still, the hope is I can still capture the essence of the various problems that everyone in this audience is interested in to some extent. So let me start with a couple of motivating examples in which this kind of trade-off study is potentially useful. So this is, imagine that this is a camera-based control system of a drone. And imagine that this is a drone with an onboard camera device, something like this. And imagine that your task here is to design and control a navigation algorithm for this drone. And one possible difficulty, engineering difficulty you might face in this kind of situation is that nowadays, this type of camera devices can produce a lot of information, much more than this type of onboard computer can handle with in real time. So the natural question arises, is it possible from the sensor data to select important information only that is relevant to your control task? And notice that this notion of importance of information is really a task dependent. The importance of information really depends on what you want to do based on that information. So for that reason, I like to consider this problem as a joint design problem of sensing strategy and a controlling strategy. And this problem has actually attracted quite a lot of attention in robotics community, for instance. And I'd like to mention that there was a very relevant workshop in robotics conference earlier this year. Right. And of course, we are also interested in understanding human decision makers. And this is supposed to be a driving task. And I took this figure from this paper. So suppose this is a driving task. And in principle, we can use all information from every single pixel of this image. But perhaps that's not what we do. Perhaps what we're doing is subconsciously selecting the most relevant information for driving the task. And I'd like to understand this, what this minimal information is mathematically. And once we understand this question mathematically, perhaps even more interesting question is actually about learning. So for instance, when we learn how to drive a car for the first time in our life, so we tend to be over careful. Like we tend to be paying attention to way too many things, like traffic signs, traffic signals, other vehicles, and pedestrians. But after some while, as you get used to it, you can do the same thing without thinking much. So there's sort of learning processes happening in your brain. But this learning process is not per se to optimize your control performance. Rather than that, this learning process is to reduce the information processing cost. And I think this is a very interesting question. But unfortunately, in this talk, I'm not going to talk about the learning aspect of this problem. And third motivating example is, this is very different. So this is related to privacy. So imagine this is a GPS navigation service. And imagine that you're a GPS navigation service provider, and I'm supposed to provide a navigation service to those who have this kind of smartphone with GPS receiver. And being a navigation service provider, you can provide a best quality of service when you know the exact location of the user. But at the same time, knowing the exact location of the user could be a quite significant violation of privacy. So what you want to do in practice is to introduce some sort of privacy filter that intentionally reduces the amount of information that is available to you, just in order to balance the the privacy and the utility of the service. And here is the similar question that arises. What's the fundamentally relevant, important information that is essential, critical for the navigation services? So there are essentially three motivating examples. They are very different from each other, but my attempt is to capture the essence of these three motivating questions, using a single mathematical optimization problem, which looks like this. So essentially, I'm interested in designing a joint sensor and controller policy, which is essentially nothing but a causal decision-making policy from X to U. And I'd like to use, in order to model this causal decision-making policy, I'm going to use this conditional probability distributions. So in my notation, the superscript T denotes the history all the way up to time T. So this X superscript T means X1, X2, all the way to Xt. So by this conditional probability distribution of this structure, essentially we can model any general class of causal decision-making policies. And we want to design this policy, and there are two objectives in this reason, of this design. First of all, we want to make sure that, first of all, this decision quality is better than something. So this is what the second line essentially means. And among all policies satisfying this constraint, I want to minimize the information consumption, which is essentially the first line. And by solving this optimization problem, and by defining this optimal value as a function of D, this is exactly the trade-off curve between the quality of decision and the information that you have to use. In this diagram, basically, I'm considering that direction to be a good direction because I want to minimize some control cost. Right, so I already explained the motivation. So for the rest of my talk, I'd like to first of all explain the problem formulation. In particular, I'd like to explain what this notion of directed information, which is an important notion in this talk. And then as a main result of this talk, I'd like to claim that this optimization problem is actually very easy to solve by means of semi-definite programming. And I'm going to explain what the semi-definite programming is and how the solution mechanism works. And then I'd like to show one application of this result to the networked control problem, which is essentially a control loop, but this feedback information must be encoded into a sequence of binary messages. And the reason why I wanted to include this application in this talk is that this gives you, in my opinion, this gives a very strong evidence that this directed information, this notion of directed information is a very, very relevant notion, quantity in our study. And then I'd like to conclude and summarize. Right, so let me start with the problem formulation. So, by the way, this is a LQG control with minimal directed information, but for short, I like to call it data-frugal LQG control. So this is conceptually, this is what we want to do. So we want to design, again, the causal decision policy from X to U, which attains a certain decision-making quality. And among all policies satisfying this constraint, I want to minimize the information flow from X to U. This is the conceptual optimization problem that I like to consider. So the natural question is, how can we measure the information flow? How can we quantify the information flow from X to U? And perhaps the natural first choice is to use the notion of mutual information from information theory. Very roughly speaking, the mutual information between random variables X and U gives you a common information bits shared by these two random variables. Mathematically, this quantity is defined by this formula, which is nothing but the entropy of X minus the entropy of X after observing U. That gives you a common information bits shared by these two random variables. And if X and U are jointly Gaussian, we have an explicit formula for this mutual information, which looks like this, where this P is a covariance matrix of X, and this is a covariance matrix of X after observing U. And our idea is to use this mutual information to measure the information flow from X to U. However, here's a fundamental problem. The difficulty comes from the fact that essentially the mutual information is a symmetric quantity, meaning that I of xu is equal to I of ux. However, if we go back to the previous slide, so we are interested in the information flow from x to u. So there should be a notion of direction somewhere. Right? So for that reason, I need to introduce another notion, which is called directed information, which is actually introduced in a context of, in a community of information theory, in order to analyze the so-called feedback channel capacity. And according to the this Massey's definition, this directed information is defined by this formula. And according to this one of the inventors' word, this quantity essentially captures the information flow from one sequence of, well, one random process to another random process. So this is not a symmetric, this is a symmetric quantity. And, yep?
Causal in some sense.
Yes, yes. And there's a very intuitive formula regarding this directed information, which is sometimes called conservation of information. So this formula is essentially saying that the total dependence between x and u can be written as an directed information from x to u and the information from u to x. And in order to understand this formula, I think the best way is, again, coming back to this feedback diagram. If you look at this feedback diagram, it's clear that there are actually two reasons why x and u are dependent on each other. One reason is because there's an information flow from u to x through the plant, through the environment, essentially. And there's another information flow through your action. So I hope that this diagram kind of convinces you that this red information flow, red directed information is something we should be looking at, because we are not so much interested in this information flow, because this information is essentially processed by the environment. Right? So this brings us to essentially this problem formation that I presented in the beginning. Right. So, so this is again, we are trying to optimize over this space of conditional probability distribution and minimize the directed information. So this is an infinite dimensional optimization problem because we have to optimize over the entire space of probability distributions. Right. So this is a formulation, and next I'd like to claim that this problem is actually, although it's in the original form it's an infinite dimensional problem, it is actually very easy to solve. So our claim is the data-frugal LQG control problem is actually a semi-definite programming problem. And let me explain what the semi-definite programming is and what's the practical benefit of this result. And finally, I'd like to mention how this result is derived. I think it's quite insightful. So first of all, what is this semi-definite programming? Well, semi-definite programming is an extremely well-behaving class of convex optimization problem that can be viewed as a generalization, natural generalization of linear programming. And in a control community over the past 20 years, per se, SDP has been an extremely popular language. And the basic philosophy behind this literature is essentially, since we have a very efficient algorithm to solve this optimization problem, we can consider this as a solution by itself. Yeah, of course, this is a problem, but at the same time, we can consider this as a solution by itself. So to some extent, we can write a paper in control community once you can formulate the control problem as a semi-definite problem. But of course, some people don't like this idea very much because you can solve the problem without understanding the problem very much. But yeah, so this is a good and bad. But in this talk, I'd like to accept that semi-definite programming is actually a good thing. So what's the practical value of this result? So I'd like to show you my favorite numerical example. So imagine that this is a satellite, and this is a spin-stabilized satellite, and this is the equation of motion of this. Omega is the angular velocity vector of this satellite. And imagine that this satellite has a very accurate onboard attitude sensor. So the satellite is able to measure this angular velocity vector very precisely. But imagine that this information must be transmitted to the ground station, and the ground station must estimate this omega within some precision, dt. And this dt could be a time-varying requirement. So for instance, you can draw this kind of pink curve, which is the requirement curve. You want to make sure that the estimation error is always below this pink curve. For instance, you want to make sure that when the satellite is in a mission phase, you want to make sure that this estimation error is small, but at some other times, this requirement can be relaxed or something like that. You can essentially draw any curve here. And the natural question is then, in order to achieve this goal, how many bits of information must be transmitted from the satellite to the ground station in order to achieve this? And interestingly, this problem can be solved by semidefinite programming, meaning that you can write few lines of Python or MATLAB code, and you can find a solution. And the solution looks like this. So again, this is a requirement curve. You want to make sure that the estimation error is always smaller than this. If I run the optimization algorithm, then you get something like this. Essentially, this bottom plot is showing is the number of information, the information bits that must be transmitted from the satellite to the ground station at every time instant. And if you do this communication, you can actually achieve this requirement. And there's something interesting is happening here. For instance, if you look at the interval around here, around 20, this value is 0. Meaning that zero communication is required. So there's no communication is required between satellite and ground station. And of course, during this phase, since the ground station is not receiving any information from the satellite, the estimation error is growing as shown in this blue plot. But that is fine as long as this blue curve stays below this pink curve. But eventually, this blue curve hits to this pink curve, and this is the time when a sort of phase transition happens. The satellites need to send a new information to the ground station so that the estimation error can be kept below this level. Right? And I hope this is an intuitive result. But again, you can solve this kind of optimization problem by writing a few lines of Python or MATLAB code. Right, so I'd like to explain how we can derive this result, just in case you're interested in a little bit linear algebra. And I believe that this derivation is a little bit insightful to understand this result. So remember that this is the problem that we are interested in. We are interested in designing this policy to solve this optimization problem. So again, this is an infinite dimensional optimization problem. First of all, we need to understand some structural property. We need to say something qualitative property about this optimization, about this optimal decision policy. Turns out that we can prove that the optimal decision-making policy is always in this form. So there's some sort of separation happening. So what this decision policy is doing is, first of all, it is observing X, but not all information is processed. This sensor mechanism is essentially selecting the most relevant information from X. And this C matrix is essentially selecting the relevant information from X. And this noise, you're actually adding noise. And this noise means that you need to indicate that to what extent, to what precision you need to measure this information. And then this output Y is processed by Kalman filter. And then this best estimate is multiplied by the optimal control, optimal feedback control gain. And then this is the way that the optimal control signal U is generated. And there are a couple of interesting observations here. First of all, the optimal policy is linear. This is a linear process. And second of all, there exists a finite dimensional sufficient statistics. Although you are allowed to remember everything from the past, but if in fact it is sufficient to remember this x hat only. This is an implication. And moreover, this 3 data processing components can be actually efficiently designed by this numerical procedure. And of course, the interesting thing is that this data selection mechanism can be optimally designed by solving some sort of semi-definite programming. And another thing I want to mention here is that, yeah. Yeah, so another thing I want to mention here is that the dimension of this observation signal y, the dimension of y is not specified here yet. And that is part of the problem. Part of the problem.
Is the Kalman fit determined? If the Kalman fit is for system parameters, you know?
Once this is determined, this equation is determined, we know how to design a Kalman filter.
It's not part of that parameter.
Yeah, right. So perhaps this is a most interesting part. So let me explain how this works. So the idea is to rewrite this optimization problem as an optimization problem in terms of this covariance, estimation covariance matrix. And as we saw, since everything is Gaussian, we can write this directed information as a function of P, like this. And if you're familiar with optimal control, LQG control theory, we know that the best control cost can be written as a linear function of P, like this. And since this is a covariance matrix, estimation covariance, and this is dependent on your sensing strategy, this evolution must satisfy this equation, which is nothing but a Kalman filtering formula. So it's not actually difficult to see that this data frugal LQG control problem can be written as a non-convex optimization problem with respect to these decision variables. But of course, this is a kind of complicated optimization problem because of this constraint, because of this nonlinear equality constraint. This is very difficult to handle with. And here's a trick that we invented, essentially. So it's based on a variable elimination. So this is the constraint, nonlinear inequality constraint, but this constraint is actually requiring the existence of C matrix and V matrix satisfying this equation. However, if we consider this red block as a positive semi-definite slack variable, we can simply eliminate this variable and replace this equality with an inequality. And then take the inverse of both sides, we arrive at this condition. And mathematically, all of these are equivalent because the eliminated variables C and V can be reconstructed by this equation. So this is a simple mathematical technique, but at the same time, this is quite powerful because this allows us to replace this complicated nonlinear equality with a linear inequality constraint, which is much easier to handle with. So if I put everything together, what I want to say is we can rewrite this original data frugal LQG control problem as a semi-definite programming problem. Although it looks a little bit complicated still, but I want to say that this is semi-definite programming. It's very easy to solve. And once you find the optimal solution P here, then from this P, you can reconstruct the optimal C matrix and V matrix, and from which you can essentially reconstruct the optimal sensing strategy. And remember that determining the right dimension of this observation signal is a part of the problem. But from this result, what we can say is that essentially by computing this rank, you can determine the optimal dimension of your observation. So there's sort of phase transition happens. If the information cost is very, very high, it is possible to have this optimal dimension is actually 0, meaning that close your eyes and sleep is essentially the optimal policy. And that kind of phase transition can be observed here through the rank dropping phenomenon.
Just the water feeling.
Yes, this is like a water feeling. Right. Right, so here's one extension. So far we have been talking about a fully observable plant, but this is another way to writing the same decision-making structure. We have an easy extension to the case where the plant is not fully observable, it's a partially observable process, and we can do the same thing here. So, right, so for the rest of my talk, I'd like to present one application of this result to the context of networked LQG control. And again, the reason why I want to do it is to to have a strong evidence that the directed information is the right quantity to look at. And notice that, for instance, that there's a notion of channel capacity, which is essentially computed by maximizing the input-output mutual information. But this is not Shannon's definition of channel capacity. Shannon actually defined channel capacity as the maximum number of symbols that you can transmit reliably. And then he proved that this quantity can be computed by maximizing mutual information. So his definition of channel capacity is more operational. So here I want to find an operational meaning of this directed information. So what I would like to consider is this problem. It's slightly different from the previous problem. So again, I have a linear plant with Gaussian noise, but this time I have an encoder here, which is at every time step, this encoder is able to observe the state vector x, but this information must be somehow encoded into a prefix-free variable binary code bus. It's a sequence of 0 and 1s. And this message must be received by this controller, and this controller must interpret this message to generate appropriate control signal U. And we are assuming that both encoder and controller have memory, and that's why we'd like to model these two objects as, again, the conditional probability distributions. And the design design purpose is, again, to minimize the data rate, which is actually so this L is the code word length, expected code word length. So for instance, what happens here is that at some time instant, the code word could be something like 101, while in the next time step it could be like 11010 or something like that. And your purpose is to jointly design this encoding and the controlling scheme in such a way that the expected code word length is minimized. So this is the data rate, and this is the definition of the data rate. And right. So unfortunately, this is a very complicated optimization problem because this is a mixture of continuous and discrete optimization problem. So it is very difficult to solve this problem exactly. But an interesting observation is that this quantity, although computing this is very, very difficult, is highly related to the directed information that I just described. So yeah, so like I explained, this is the original problem that I like to solve, but I just explained, solving this problem is very difficult. So what I'm going to suggest is to take an alternative path. So what I'm going to do is to replace this objective function with a directed information. So that's what I'm going to do here. I'm replacing the original problem with something simpler, which I know we know how to solve. This is essentially semi-definite programming. And then this solution is interpreted back in the original context. And the solution obtained this way is suboptimal, unfortunately. But the interesting thing is that the performance loss is actually bounded. So, like I explained, this solution to the data-frugal LQG control problem looks like this. But this problem cannot, this architecture cannot be implemented by this binary network control problem, because all the signals here are continuous variables. So you need to introduce some sort of quantizer and encoder somewhere. And the basic idea is the following. If you introduce a quantizer, you are basically introducing a quantization noise. And what I'm going to suggest is this: it is correct. The optimal way to design this quantizer can be done by designing this quantization step size in such a way that the quantization noise looks like the optimal Gaussian noise you are adding. So essentially, you're replacing this Gaussian channel with a quantizer. So this is something you can implement. So this is essentially the encoder, and this is actually the controller. So I have a simple numerical simulation to demonstrate this. This is a classical control problem. This is an inverted pendulum, and this is observed by a camera, but this information must be fed back to this actuator through these binary messages. And if you do this design, this is just a design, and this is a code word designed based on Huffman code, and this is the feedback signal. And if you run this simulation, essentially this plot is showing, plot is showing is that our prediction is correct. So we can achieve this data rate, which is very well predicted by directed information. Right, so this is essentially, through this example, what I wanted to show is that directed information is a very meaningful quantity to describe the fundamental limitation of the data rate that you need to achieve certain control performance. Right, so to summarize, in this talk, basically, I formulated an LQG control problem with minimal directed information, and essentially claimed that this problem is very easy to solve by semidefinite programming problem, and also discussed the physical meaning of this notion of directed information. And there are, of course, many remaining technical questions. Well, the first one is this, of course, at this moment, what we can do is only LQG control, an LQG system. What happens if the environment is not LQG? And also another very interesting question is, like Chris quickly mentioned about the learning. What if you didn't really know about the environment? How can we still do the achieve the data frugality? And I think all these questions, and I think the theme of this workshop is actually very, very important and interesting. It should be very important in the control community as well. So I think I'm really looking forward to working with, in the future, a neuroscientist or a physicist and a biologist in a related domain. And with that, I'd like to conclude my talk.